The narrative opens with a patient, silent machine located far from Earth. In the blackness of space, the enormous mirror unfolded like a silver flower. The James Webb Space Telescope gradually rotated its potent equipment in the direction of 3I/L, a tiny, swift visitor. Webb was staring at more than just another comet at that precise moment. It involved researching an item that had nothing to do with our solar system. Before passing momentarily through our cosmic neighborhood, this visitor had journeyed through deep space for millions, perhaps billions of years. Thanks to Webb's infrared vision, scientists were able to obtain new data and photographs that showed previously unseen details, providing humanity with a unique view of material generated around another star. A comet appears to most people as a fuzzy dot with a bright tail. However, a comet is seen by scientists as a frozen record of the past. There are hints about the environment in which it evolved inside its ice and dust. Our solar system's comets reveal the origins of the sun and planets. However, an interstellar object such as 3I/ATLS is much more unique. Material from an entirely different star system is carried by it. The Webb was created for situations like this. It can detect heat, gases, and compounds that are invisible to regular telescopes because it can see infrared light. When Webb concentrated on 3I/Atlas, it identified glowing fingerprints of gases surrounding the object, particularly carbon-based molecules. Webb recorded spectra, which are detailed light patterns, in addition to gorgeous photos. For many compounds, these patterns function like fingerprints. Scientists were able to identify the gases surrounding the comet by examining them. According to the results, there was a significant amount of carbon dioxide and other carbon-rich elements in 3I/Atlas. This was significant since it suggested that the comet originated in a very frigid area of space. These volatile substances were able to freeze in such conditions and stay confined for billions of years. The chemistry seen near 3I/ differed from that of many known comets, indicating that its home system may have had a distinct evolution. Webb's findings were not isolated. Other telescopes in orbit and on Earth were observing the comet at the same time. Some photographed it in visible light, revealing a tiny, luminous core surrounded by a gentle cloud of dust. Others captured the comet's movement across the sky, producing time-lapse photos that gave the comet an animated appearance as it sped across space. Scientists were able to obtain a more comprehensive understanding of the object by combining all of these observations. Like puzzle pieces slowly fitting together, each telescope showed something unique. The comet's behavior was among the most unexpected observations made by scientists. 3I/Atlas demonstrated strong jets firing material outward rather than dispersing gas and particles equally. These jets appeared strangely shaped or aimed in unexpected directions in certain pictures. This implied that the comet was rotating and that some parts of its surface were more active than others. Certain alterations occurred rapidly over the course of hours or days, suggesting that the nucleus was rotating more swiftly. Compared to many ordinary comets, scientists were able to assess the comet's subsurface structure because of these movements. Scientists were also able to thoroughly examine the dust because of Webb's infrared data. When the sun warms dust grains, they shine a little, and Webb can pick up on that subtle heat. Researchers were able to determine the size and makeup of the dust particles by examining this glow. Some seemed younger and smaller, while others were older and more compact. This information clarifies the duration of the surface's exposure to space and the force with which material is being discharged. This is significant for an interstellar object since it has lived far from any star for most of its existence. 3I/Atlas were more active as they approached the sun. A brilliant coma was created when frozen gases transformed straight into vapor, forcing particles outward. Observations revealed abrupt bursts in which the comet's jet patterns changed after it momentarily brightened. These occurrences indicated subsurface pockets of volatile substances that were abruptly revealed. Scientists were able to comprehend how heat moves through the comet and how its structure responds to such a lengthy voyage through frigid space by observing these changes. Scientists from all across the world worked fast behind the scenes. Because interstellar objects are fleeting, every observation matters. Teams checked each other's performance, exchanged data, and coordinated schedules. This international collaboration is essential to modern astronomy. This study was successful because of its capacity to react fast and integrate observations from various sources. It demonstrated how ready the scientific community is to investigate uncommon and rapidly moving items. There was still one major question. What was the source of 3/A? It developed in a frigid outer area of another planetary system, according to the chemical indications. Carbon and other elements necessary for complicated chemistry might have been abundant in that area. This presented intriguing opportunities. The fundamental components of life may be widespread throughout the galaxy if such materials are prevalent around other stars. This supports the notion that the chemistry required for life is not exclusive to our solar system, even while it does not imply that life exists elsewhere. How the item got out of its home system was another mystery. It was most likely ejected by gravitational forces, perhaps by passing stars or massive planets. It spent a very lengthy time drifting through interstellar space after being evicted. It was subjected to intense cold and cosmic radiation during that voyage. However, a large portion of its original content survived despite this difficult journey. Scientists were captivated by this harmony between preservation and change, which provided hints about how interplanetary objects age over time. Even additional depth was added by other kinds of observations. Faint energy emissions from interactions between the comet's gases and the solar wind were observed by certain equipment. This demonstrated the comet's reaction to the charged particles coming from the sun. By examining these exchanges, scientists discovered more about the comet's material loss and the level of energy in its surroundings. Every light spectrum conveyed a distinct aspect of the narrative. The pictures that were made public attracted people's attention all across the world. They displayed delicate dust structures, luminous clouds, and motion that seemed to be frozen in time. These pictures depicted actual physical characteristics, even if they had been altered for human perception. Everyone was reminded that this was a visitor from another star system, not merely a far-off object. It was difficult to estimate the comet's nucleus size. Direct view of the solid core was obscured by the brilliant cloud of dust. However, scientists calculated that the nucleus was probably several kilometers broad by examining brightness and mobility. Its size made it easier to understand how powerful its jets were and how much material it could discharge without disintegrating. Comparing it to comets from our own solar system was made easier by these measurements. As data analysis progressed, scientists identified both common and uncommon characteristics. Certain elements of 3I/as exhibited comet-like behavior they had already studied. Some didn't. Its dust behavior and chemical balance were particularly noteworthy. This served as a reminder to scholars that not all interstellar visitors can be represented by a single object. Each has a distinct past that shapes it. Nevertheless, Webb's findings offered a solid benchmark for further research. The effectiveness of these observations demonstrated how crucial preparedness is. The ability of contemporary survey techniques to identify anomalous objects early on is improving. Scientists now have more time to investigate them. Webb's contribution demonstrated how strong space telescopes can react to uncommon opportunities. Some scientists are already planning ahead, envisioning spaceships that could eventually pursue and closely examine such things. Though challenging, the concept no longer seems unattainable. For the general public, the connotation was clear and potent. Humanity had made remarkably detailed observations of stuff from another star system. It served as a reminder that our solar system is a component of a much larger galaxy. These encounters foster a sense of interconnectedness and curiosity about the cosmos. 3I/ATL's narrative is far from finished, despite the fact that it is currently heading away. For years, scientists will examine the data. They will improve their models by comparing them to upcoming interplanetary travelers. Every investigation deepens our understanding of the formation and evolution of planetary systems. Ultimately, the photos taken by the James Webb Space Telescope represented more than just scientific information. They provided a window into a different location, era, and star's past. They demonstrated what can happen when cutting-edge technology and human curiosity come together. This event will be recognized as a significant step in discovering worlds beyond our own, as the Webb continues to fulfill its mission and attract more users. For a moment, we were prepared to examine the visitor that the cosmos had sent. Scientists were aware that every hour counted as the comet continued to move away from the sun. Interstellar objects do not slow down. They go through, briefly show themselves, and then vanish once more into the pitch-black void between the stars. This increased the value of the information gathered by the James Webb Space Telescope. Every pixel, every dim glow recorded with infrared light, was a message transmitted over unfathomable distances. Knowing that this chance might not present itself for many years, scientists handled the data with care, double-checking computations and comparing outcomes. The way 3I/Atlas appeared to be both peaceful and violent at the same time was one of its most intriguing features. It appeared serene from a distance, moving across space in silence. However, it was active up close, releasing energy, spewing gas and particles, and responding violently to sunlight that it would not have previously seen. This scientists were reminded by contrast that objects in space are not static rocks. Their bodies are dynamic and ever-changing, molded by their surroundings. When it entered our solar system, that environment abruptly changed for 3I/Atlas. The comet most likely lived in near-complete darkness for millions or possibly billions of years prior to coming here. It is unimaginably cold between stars. There, the temperature is just above freezing. Ice stays frozen solid, and chemical processes slow down in the setting. That long-frozen material started to awaken when 3I/ with a TLS got closer to the sun. The shimmering cloud Webb saw was created as trapped gases inside the ice began to escape, pushing particles outward. The comet appeared to be breathing for the first time in a very long time. The speed at which this activity started particularly piqued the interest of scientists. Even though it was still far from the sun, the early indicator indicated that 3I/LS responded vigorously. This suggested that some of its ices were very heat-sensitive. This sensitivity lends credence to the theory that the comet originated in an extremely cold area of space. Such volatile compounds wouldn't last long in warmer climates. This information assisted researchers in determining the object's potential birthplace. The activity's apparent unevenness was another noteworthy element. The jets did not come from every angle. Rather, they appeared to be concentrated in particular places. This implied that the surface of the comet was uneven. While some areas had thin layers or fissures that made it easier for gas to escape, others were probably coated in a thick, solid crust. The comet's behavior is shaped by these weak areas becoming increasingly active over time. The variations in brightness observed by telescopes were also explained by this uneven surface. Scientists observed that the jets seemed to swing back and forth as they simulated the comet's spin. This motion implied that the nucleus was rotating and might have been swaying a little due to unequal material outflow. A comet's rotation can be gradually altered by this mechanism, sometimes increasing or decreasing its speed. Such forces have the potential to even shatter a comet over extended periods of time. Scientists gained insight into how tiny bodies change under stress by observing these impacts in real time. 3. I/TS released the dust. While some particles were bigger and heavier, others were microscopic and resembled smoke. Scientists were able to comprehend how the material was discharged thanks to the variety of particle sizes. While greater outbursts can carry heavier boulders, gentler gas flows produce fine dust. Warm dust could be detected even when it was faint thanks to Webb's infrared sensitivity. This made it easier for scientists to gauge how much material the comet was shedding. In general, there was also interest in whether the comet displayed indications of organic compounds other than simple gases. Carbon-containing molecules are known as organic substances, and they are essential components of life. Webb's tools are able to identify such molecules, and preliminary research suggested the possibility of complicated chemistry. This implies that the components for life can form in a variety of settings, even though it does not imply that the comet contained life. Scientists are excited by this concept because it lends credence to the hypothesis that life-friendly chemistry may be prevalent throughout the galaxy. The public's reaction to Webb's observation was swift as word got out. People expressed wonder at the prospect of studying material from another star system, shared pictures, and asked questions. For many, this was the first time that the idea of interplanetary visitors seemed more plausible than speculative. It was no longer merely science fiction. It was something that people could see, examine, and comprehend, at least somewhat. Teachers described how telescopes operate using the pictures. Students discovered how objects undetectable to the human sight can be shown by infrared light. The brilliant colors and shapes served as inspiration for artists. Authors conjured up tales about the comet's origins and what it had witnessed during its arduous voyage. 3/It became more than just a scientific concept in this way. It began to represent curiosity and adventure. Discussions became more in-depth within the scientific community. Researchers disagreed about how common or uncommon this object might be. Was 3I an uncommon anomaly, or did it depict a vast number of similar objects floating between stars? The response is significant because it influences how scientists calculate the quantity of interstellar objects that are now traveling through our solar system. Our solar system may be visited more frequently than previously believed if objects like this are widespread. According to some simulations, billions of tiny bodies that were expelled during the turbulent early phases of planetary formation may be wandering the galaxy. The majority would never be seen. Only those traveling near enough to the Earth and Sun would be noticeable. Therefore, what we see is really a small sample. Every interstellar object under study contributes to the improvement of these models, enhancing our comprehension of the interactions and evolution of planetary systems. There was also talk on how Webb's work might be enhanced by future telescopes. Despite its great power, the Webb is not made to pursue moving objects for extended periods of time. Telescopes or spacecraft designed expressly to track and follow swift interstellar visitors may be part of future missions. Some ideas include using enhanced propulsion to deploy probes on short notice and intercept objects soon after they are discovered. Although these concepts are difficult, Webb's observations make them seem more doable. The comet became fainter over time. As it got farther from the sun, the jets became weaker. The coma gradually waned. 3I/Atlas eventually got too dim to be seen with most telescopes. However, the crucial job had already been completed at that point. The information had been gathered. The pictures had been saved. The actual travel was now taking place in offices and labs where scientists were still analyzing and interpreting their observations. 3I/Atlas comets from our solar system were compared by certain researchers. In an effort to find patterns, they searched for parallels and discrepancies. Others concentrated on simulating its internal organization. Some investigated how its surface might have changed over time because of space radiation. Every strategy contributed a new piece to the jigsaw. Whether interstellar comets like 3II/Atlas may have previously supplied material to newborn planetary systems was one particularly intriguing subject. Such objects may deposit organic molecules on nascent planets if they frequently pass through systems. This material exchange may have galactic-scale effects on chemical evolution over billions of years. Even though this theory is still theoretical, observations like these offer the information required to investigate it. Really, the significance of patience in science was further emphasized by the tale of the 3I/AT. Seldom are discoveries made instantly. The photos taken by the Webb were just the start. It takes time, careful consideration, and occasionally dispute to comprehend them. Scientists have to test several hypotheses, question presumptions, and update their findings. Images become knowledge through this gradual process. The answer was humble as well. Even with cutting-edge equipment, scientists were aware of its limitations. There would be some unanswered questions regarding the interior of the comet. A few chemical fingerprints were weak or unclear. However, even partial information was useful. It pushed the limits of knowledge and promoted the creation of more advanced instruments. The Webb will definitely see a lot more far-off items as it continues to function. However, 3I/ATS will always be remembered as among the initial. Visitors from other planets were examined with such accuracy. It came at a period when humankind finally acquired the means to examine things up close. Such interactions were unimaginable to previous generations. They are now starting to materialize. 3I/AT keeps traveling into the silent blackness of space. It won't come back. It will wander through gas clouds, pass other stars, and stay frozen again. Just as it held the memory of its birthplace when it came, it also holds a record of its experience with our sun. It uses motion and time to link far-flung regions of the galaxy. The experience inspires and imparts knowledge to humanity. It serves as a reminder that we are not alone. The galaxy is accessible from our solar system. We can get stuff from far-off stars, and we can learn from it if we have the appropriate resources. The James Webb Space Telescope accomplished more than take pictures. It provided a look into the past of a different world. Future generations might consider this to be a pivotal occasion. A time when interplanetary objects became important scientific messages instead of uncommon curiosities. A time when our comprehension expanded somewhat and the cosmos seemed a bit smaller. And 3I/AT passes on, silent once again, someplace beyond the view of any telescope, leaving behind the questions it raised, the heat it emitted, and the